Okay, and finally, our next speaker will be Max Wiesner, who will talk about asymptotic weak gravity conjecture for open strings.
So thank you very much, Irene, and thanks also very much to the organizers giving me the opportunity to come back to my home swamp in Madrid. And indeed, I will talk about some work I did in collaboration with this Hamburg gang earlier this year, which is about the asymptotic weak gravity conjecture of open strings. And so as the title suggests, it's about the weak gravity conjecture. And I think there was already Matt introducing it in his colloquium, and I think it's familiar to most of the people. What is the statement? That in, for instance, the U1 gauge theory coupled to gravity, there must exist a super extremal state, which essentially is the statement that it should have a charge to mass ratio that is higher than the extremal charge mass ratio of a black hole. The motivation is, roughly speaking, like a bottom-up motivation, is that extremal black holes should be able to decay. Alternatively, at least if we deal with particles, one can say that the state with the highest charge to mass ratio should be self-repulsive in order not to form bound states. This is called the repulsive force conjecture, which essentially states that the Coulomb force should be larger than the gravitational attraction, or in the presence of scalar fields, the Coulomb force should be bigger than the sum of the gravitational attraction plus any Yukawa force between them. There are stronger versions. So in principle, the normal weak gravity conjecture just requires a single state that is super extremal. But there are stronger versions that were also introduced earlier in Matt's colloquium, like the tower weak gravity conjecture, which state that there should be an infinite tower of states satisfying this weak gravity, the super extremality condition. And one of the motivations for this is that it should be consistent under KK reduction, the weak gravity conjecture itself. So one can then ask, okay, how do we prove this in a theory of quantum gravity? And one can search for weak gravity conjecture states. And these can either be small black holes that, due to, for instance, alpha prime correction, become super extremal themselves, or super extremal particles with mass lower than the Planck scale or whatever quantum gravity cutoff you have. And then the tower weak gravity conjecture actually gives a constraint on the spectrum of massive states in the EFT. So in this talk, I want to consider the asymptotic weak gravity conjecture, which is the weak gravity conjecture in the limit that we take the Young-Mills coupling or the coupling to 0. And then combined with the Swampson distance conjecture, it tells us that if this limit, this weak coupling limit, is an infinite distance limit, there should be a tower of super extremal states that becomes massless asymptotically. And so we can look in these limits, in these asymptotic limits, in these weak coupling limits for asymptotically massless super extremal states. So there is some evidence already for this tower weak gravity conjecture, which comes, for instance, from closed string U1s in 5D n equals 2 of 1 of 4D n equals 2, which includes where the states are tower of charge VPS states that become massless at infinite distance, or in perturbative heterotic gauge series that discussed in, for instance, in 6D n equal 1, or in 4D equal 1, where the states are, the super extremal states are towers of string excitations, and the existence can be checked as is explained in this series of papers due to modularity of the elliptic genus for a critical string, the perturbative heterotic string. One can also then ask, what about open string gauge theories, such as 7-brane gauge theories in F theory, which is the topic of my talk? Are there also, what kind of states do we have there? For instance, in 4D n equal 1, we don't have BPS states, which would be the candidate here. Are there also more general limits that are not just perturbative heterotic limits? Are there also towers of string excitation? This was suggested in this paper, and this is what this paper of my talk will be about. So in this talk, I will focus on weak coupling limits in 4D n equal 1 F theory compactification. So I take F theory on an elliptically fibered Calabi fault, and have some gauge theory with some gauge group G, which I can take for simplicity to be U1, realized on some divisor in the base V3 with the gauge coupling, the inverse gauge coupling given by the volume of the divisor that is read by the 7 branes. And the weak coupling limits now correspond to limits in Kähler modular space, such that the volume of some of the devices that are read by the by the 7 brands goes to infinity. So the question is here, what furnishes the tower of super extreme states? The first candidate would be a KK tower, but they are not charged, so this is not a candidate. But the second candidate would be excitations of the 3 brane wrapped on the curve C, essentially such that C and D have the divisor where the gauge group is realized have non-zero intersection, such that on the string worldsheet theory, is like Timo explained, and I think Luca also mentioned, the string which has fermions charged under G, which then leads to particle-like excitations that are also charged under G if we have a perturbative string description. So this is the candidate tower on which I want to focus in my talk. So can this work in principle, like in this F-theory limit? And it does, at least in emergent string limits, as like these kind of limits that were discussed in these papers. When the base B3 itself has a rational fibration, we can look at the D3 when on a generic fiber that gives rise to a critical string, which if it actually is charged under the gauge group is a critical heterotic string, or which if it has charged 0 modes. And we can consider a gauge theory on the base B2 of the full F-theory base and take the weak coupling limit, which would be here morally just volume of the B2 going to infinity. And in this case, the existence of a tower of marginally super extremal states, so really which marginally satisfy this super extremality bound, is as shown in these papers, ensured due to the modular properties of the elliptic genus. And in this case, as we studied in this paper, also the repulsive force conjecture and the weak gravity conjecture also have been studied slightly away from the asymptotic limits, including one loop corrections in terms of the heterotic gauge coupling. So, but one can ask, okay, this is one class of models. We saw in the previous talks that there are more general strings that we can obtain from D3 branes wrapped in F-theory. So what about these settings? So first we need a classification of weak coupling limits in terms of these strings. We somehow need to say, okay, if we have a weak coupling limit, what is the candidate string that might furnish the tower of super extreme excitations? Then exactly, so we first give this classification, then we identify this perturbative weakly coupled string that are charged under the gauge theory, and then we can check if the weak gravity relation is actually satisfied for the excitations of this candidate string. So the main results of the remaining of my talk is to provide a classification of weak coupling limits in terms of weakly coupled EFT strings that were briefly mentioned, or that were mentioned in Luca's talk and then also in Timo's talk. And I want to show that in such limits, the tower weak gravity conjecture is actually only satisfied by string excitation if the species scale, which was discussed today earlier by Alvaro, is set by the tension of this weakly coupled string, and then argue that this means that the tower weak gravity conjecture is only satisfied by string excitations for the emergent heterotic string limits that I was discussing before, that I mentioned. Okay, there it is satisfied, and I want to show that this is the only way where it is satisfied. So EFT string limits, you saw in Timo's talk, so I think a very similar slide, but okay, it's the same topic, so it better should be similar. So an infinite distance limit in field space of a 4D n equal 1 or 4D n equal 2 EFT is characterized by an unbroken axionic shift symmetry, which, for instance, in n equal 1, which is the topic of this talk, can be for the chiral fields, which are just an saxion plus the imaginary part of axion. And in this infinite distance limit, there's just a continuous shift symmetry that is unbroken. So due to the shift symmetry, we can dualize, as was also explained by Luca, we can dualize the axion into a 2 form, and we can consider the strings that are charged under this 2 form. And one can look at the associated 1/2 PPS cosmic string solutions for a string of some charge EI, and then look at the back reaction, which induces a logarithmic profile, which is enforced on us by the condition that this string should induce the monodromy when going around it. So we get this kind of profile, and close to the string core, as was, I think Luca had the nicer pictures, close to the string core, we can realize the infinite distance limit. Now an EFT string is a string in which the instanton charge under the shift symmetry induced by the string become suppressed. Exactly. So how does this look if we specify to F theory in 48 equal 1? The chiral fields that I want to look at are here Kähler moduli, complexified Kähler moduli. So what divisor volumes plus C4 axion. The instantons are Euclidean D3 branes, and the strings are D3 branes on curves in the movable curve, as explained by Timo. So now the EFT string limits is a limit in which the subset of the generators of the effective cone. So if the subset of the generators of the effective cone have a volume that diverges like this, while all other other generators of the effective cone remain finite. And then one can also define primitive EFT string limits, where essentially this subset I consists just of a single generator of the effective cone of B3. And so the distant axonic string conjecture that was put forward in one of these papers says that any primitive large volume limit for generator D can be generated by an EFT string on the dual generator of the movable cone. So this I want to use, or with this we use to classify recoupling limits. And therefore we look at a gauge theory on some divisor D in the effective cone of B3. And in general, this will be a linear combination of generators of the effective cone. And we ask, can we take the primitive string limit for one of these devices? So can we take a limit for these devices where we just blow up a single divisor volume? And in this case, the D3 brane on the dual curve becomes weakly coupled, which then is the candidate for the string that should satisfy, or whose excitation should satisfy the repulsive force condition or the weak gravity condition. And when we have this, we can check explicitly if this repulsive force condition is satisfied. Like one caveat is that not the primitive EFT string limits does not necessarily exist in every Kähler cone chamber, because it might be that we need to go through flop transitions, about which we heard this morning by Leon, to reach actually the primitive EFT string limit. So at least to me, it is not really clear what happens at a flop transition in an n=1 theory. So, and which then also means that if we stay within a single EFT within a single classical Kähler cone chamber, the EFT string spectrum might change because we might need to go into other cones. So in this talk, I want to avoid all these floppy issues. I just want to look on a single Kähler cone, so I know how to describe the back reaction because I don't need to go through any flop transition. And so how can we classify the EFT strings and their corresponding limits? So the problem is that the volume of the devices cannot be scaled independently because they depend quadratically on the Morricone volumes. So, but the volume of the Morricone generator, so the curve volumes, they can be scaled independently. So just expand the Kähler form in terms of the Morricone generator volumes, and then we can just play around with the Morricone generators. And in this way, we want to classify what we call quasi-primitive EFT string limits. These are obtained by fixing a Morricone generator, so some C0, and consider the limit V0, which is just the volume of this one generator going to infinity. Then co-scale any other volume of Morricone generator in such a way that all the devices in the set I that grow asymptotically in this limit grow homogeneously. And in such a way we do the co-scaling that this set of homogeneously expanding devices is minimized. So we try to find what is the minimal set if we say the Morricone volume of a single Morricone, if we send the volume of a single Morricone generator to infinity, what is the minimal set of devices that we need to blow up in this limit in a homogeneous way such that we don't have different scalings. And we need of course to ensure that while doing this co-scaling, no effective divisor asymptotically vanishes, because then we again don't know is our n=1 description valid. If this procedure leads to a homogeneous limit for a homogeneous growing limit for the divisor volumes in I, we get something that we call a quasi-primitive EFT string limit. And then we can write down this classification that any EFT string that is dual to that is obtained to which we associate this quasi-primitive EFT string limit associated to this Morricone generator dual to a scalar cone generator, because these are just dual curves, the EFT string is obtained by a D3 brane that wraps a curve that is either the squared of this dual scalar cone generator, or which is the product of this dual scalar cone generator together with another scalar cone generator in case J0 squared is equal to 0 and there wouldn't be any curve in the class to consider. And now for a curve of this form, we can define this topological quantity, which just tells us if the which tells us whether the intersection of this curve with one of the devices that it is the intersection of is 0 or not. So a quasi-primitive EFT string limit does come in 3 classes, because these two theta functions can either take the value 0 or 1. So for any quasi-primitive EFT string, this Q can either take the value 0, 1, or 2. And so the crucial result is that for primitive EFT strings, the qualitative behavior, and primitive, I mean that just to recall that there's a single device, a single generator of the effective cone blowing up. The qualitative behavior of the weak coupling limit only depends on this value of Q. That's what we're going to show. So the importance of Q manifests itself in the following result, which is that in the limit introduced by a primitive EFT string, the volume of B3, so of the base B3, factorizes in such a way, which means that at the bottom of it, we have a leading component that is just the field, the chiral field dual to our EFT string that arises to some order that it's a polynomial in our real field, and the order of the polynomial is 1 plus Q, where Q is this factor introduced initially, and the EFT limit is just the volume of the divisor, which is just the real part of T0 going to infinity, while the other remain finite. This is just a primitive EFT string limit. So accordingly, the scalar potential in my scalar sector is asymptotically of this form, just log T plus T0 plus something, and with the prefactor minus 1 plus Q. And we can now consider a gauge theory on a divisor that contains this one single scalar effective cone generator that blows up in the primitive EFT string limit, such that the gauge coupling of this guy becomes small in the limit I consider. So one can then look at the 4D effective action. It takes this form, and this is indeed a weak coupling limit for the gauge theory, and a weak coupling limit also for the EFT string on this curve Cj, which is J0 squared or J0 dot J1. And this is an action that is very reminiscent of the heterotic string at weak coupling, which would be the case Q equal to 0, where we would just identify this T0 as the heterotic axial dilaton. So one can now ask the question: if we have a general string on such a curve, can the excitations of this string furnish the superextremal tower? And we can first see that there's a rough parametric dependence of the string tension, where this is the weak gravity conjecture scale, which is the one that is relevant to check for superextremality. And this is the correct behavior for that, since they agree, this is the correct behavior we would expect for a tower of superextreme state. That was also stressed in these papers already. But what about the order 1 factors? So let us assume that the EFT string has particle-like excitations, that we can do a heterotic-like quantization of this form, where this is just some vacuum energy. This is the tension of the EFT string. This is the mass of the excitation. This is some excitation level. Then the modularity of the elliptic genus tells us that the maximal charge of the excitation level is given at some excitation level n is given by such a condition, such that we know there are actually states that are charged at a certain level. Thank you. And we can explicitly evaluate the repulsive force condition. And going through all these steps, I don't show them to you because it's just a bit of algebra. Explicitly evaluating this for primitive Q string tells us that we get that the left side and the right side behave like this, and we see that this is only satisfied for the Q equal to 0 string, which is the critical heterotic string. So one may wonder now, is this assumption actually valid, or is there something happening to the quantization condition? But I want to argue that actually this is not a surprise, because we want to look we want to compare the weak gravity conjecture scale, lambda weak gravity, to the species scale in this case. So this is how we want to explain this mismatch. So we want to say that the assumption of a particle-like excitation spectrum, like as we have for a perturbative heterotic string, is actually not justified for Q not equal to 0. So therefore, we compare the string tension, which is of the order of course, of the quantum gravity scale, to the quantum gravity cutoff, i.e. the species scale, which was discussed in Dieter's talk and also in Alvaro's talk. So of course, the species scale, as was stressed also in both talks, I guess, is different depending on the kind of tower we have. We either have light string excitations, where it's roughly given by the string scale, or for KK tower for n compact dimension, it is given by the mkk over m Planck to some power. So let us get some geometric intuition. For the Q naught string, we have this vibration of B3 itself, which is rationally fibered. And the limit is just we shrink the fiber to 0 and expand the base. So the KK tower in this case would be like of the 4-dimensional base, 4 real dimensional base, and one can evaluate the roughly where one can just plug in the numbers and get this. Then in the Q equal to 1 string, we have a different kind of vibration. We have a surface vibration over a P1. And in this case, the EFT string, the curve sits in the generic surface fiber, and the limit is where we take the base volume C0, this shouldn't be called C0, the P1 to infinity, and such that the KK tower would be a KK tower for the decompactification to D equals 6. And for the Q equal to 2 case, I cannot really draw a picture. It's a general curve in B3, and we would have a KK tower that would be a full compactification to 10D. So, and we see that only for Q equal to 0, the species scale is actually set by the string, because only in this case, the string species scale is below the scale associated to the KK tower. So for all other cases, the species scale of the KK tower, either for 2 or 6 dimensions, is at the order, which is this case, or below the species scale for the string. So neither of these cases, Q equal to 1 and Q equal to 2, is the species scale set by the string. So what does this mean? For the Q equal to 0, we have a genuine 4D weakly coupled gauge theory, because we stay in 4D, because the species scale of the KK decompactification is way above the string tower. So we really have an emergent string limit, a very clean emergent string limit, because there's no KK tower that interferes with the string scale. And in this case, as I showed, the weak gravity conjecture and repulsive force conjecture agree, and it is satisfied by the string excitation. This was already in the previous case. For Q equal to 1, we have effectively a decompactification to 6D. We have a gauge theory effectively in 6D, which has a weak gravity scale really of the order of the species scale for this decompactification, which is also the order of the string. So the 6D string and the gauge theory are then not weakly coupled anymore, because we don't take an additional 6D weak coupling limit. And the string does not actually lead particular excitations for the EFT, because for the 4D EFT, because any excitations would be already above the species scale. So one would need to re-evaluate the weak gravity conjecture for the strongly coupled theory in 4D, which we did not attempt, but just this repulsive force condition that I applied naively on my previous slide I think is not valid, because we don't really have a weakly coupled 4D description for the string. But we have instead a decompactification limit to 60, which is really clean, because there's no additional string tower interfering with the decompactification. For Q equal to 2, the gauge theory becomes an 8D defect theory in a 10D theory, because it's just a 7-brane theory in the full type 2B theory. And here the EFT string tension, hence the weak gravity scale, is way above the KK tower. Here we don't even have a string in higher dimension, because we resolve the entire D3 brane. And the gauge theory and the gravity decouple entirely. So because roughly speaking, the weak gravity scale is way above the higher dimensional Planck scale. And then one would expect that the weak gravity condition should become trivial. And indeed it does, because here we have super extremal states, meaning that they have a charge mass ratio which is not just marginally of order 1, but actually diverges in the limit. And we get a decompactification. So this is then really a decompactification limit to 10D, and which is again clean, because we don't have any string excitations that interfere with our decompactification to 10D. So one then might ask, okay, what about other EFT, non-EFT string limits? One can make a similar classification. I won't go into this. There are then two possibilities. We either have a weak coupling limit for gauge theory that becomes a defect theory in 10D or 8D, which is similar to the Q equal to 2 string, or a weak coupling limit that becomes a strongly coupled theory in 80, which is similar to the Q equal to 1 EFT string. But in summary, the EFT string excitations only satisfy the weak gravity conjecture if A, the solitonic EFT string, is the heterotic string, and the gauge theory can also be identified with the perturbative gauge theory in the dual heterotic duality frame. And in this Q equal to 1 or in this Q equal to 2, we don't have string excitations coming from this EFT strings that would satisfy at least the naive weak gravity conjecture, whatever one had to do. So these are just my conclusions. So the 3 points I wanted to make: I considered weak coupling limits for open string gauge theories and F-zero compactification. I classified the weak coupling limits in terms of the EFT strings, i.e. the 3 branes. We found 3 types of curves that depended just on the value of this one topological quantity Q. We have 3 different types associated of behavior of the species scale relative to the weak gravity scale. So here it's just marginally below the weak gravity between the species scale, which is the string scale. Here it is of the order or above, and here it's way above. And as I said, the tau weak gravity conjecture is only satisfied by string excitations for Q equal to 0, i.e. the heterotic string, and both other limits, either non-weakly coupled, essentially non-weakly coupled theories in higher dimension, or a higher dimensional defect theory. Thank you very much.
Okay, thank you so much. Any question? Okay, see Matt and Tom.
Hi, nice talk. So one question I had, in these cases where you say that the string excitations don't satisfy the tau weak gravity conjecture, do they asymptote to the extremality bound at large charge, or?
Not even that. So just the order one coefficient doesn't match. So you would have again like a tower, but in the heterotic string you have like, okay, something asymptotes to the asymptotes to the extremality bound, and here we would be off by an order 1 factor.
Okay, so I guess that's interesting, right? Because we know that black holes should exist far out, and so I guess that's suggesting that these string excitations at large charge do not represent the extremal black holes. There must be some other states.
I guess that's correct. And I mean, I didn't go much into how to resolve this issue, because I think, for instance, the Q equal to 1 case, the 60 case, this assumption that we have this perturbative string excitations, which just work like the heterotic string. I think this is not really valid there. We really would need, I mean, it's already in 60. If you don't have the heterotic weak coupling limits, you have to do something that's more difficult, and I actually don't know how to do that.
Yeah. Okay. Thanks.
Yeah. So I have a couple of questions. I think let me start with what I think is the simplest one. It sounded to me like you were claiming that you don't think states that lie above the species scale can be interpreted as states that satisfy the WGC. Is that a correct statement of what you were saying, or did I misunderstand?
No, that's not what I'm saying. I'm just saying that this should not be like particle-like excitations of a thing. I mean, it can be black holes as well that satisfy the gravity conjecture above the species scale.
Well, there can even be weakly coupled things like winding states of strings. So what would you say about those?
I guess, yeah, if you can show that they are there, like for instance, if you take an easier setting with more supersymmetry and just take, I don't know, heterotic on K 3 times S1, and then you have winding states. I think these can for the U1 they can satisfy. But here in this case, I don't have a KK U1, or like I don't really have winding states that can play the role there.
Right. Okay. But in principle, we agree that states could be above the species scale and still obey the bound.
Yes.
Okay. Okay. Right. So then you're always working in these asymptotic limits. So I guess it's a little hard for me to compare to some of the examples I had in mind. But like the example that I mentioned yesterday, if I have the standard model on D7 branes, I have these axion strings that are D3 branes wrapping a 2-cycle. Is your claim just that we cannot calculate the spectrum of excitations of that string because it's strongly coupled, or are you making a stronger statement than that?
So I'm saying first that this string does not just behave like the perturbative heterotic string,
Sure.
because we're really above, and just this naive statement, or like I wouldn't expect any state that are actually in my EFT coming from this string, because everything is above the species scale. Above the cutoff, I'm effectively having a higher dimensional 60 string that is not weakly coupled. I don't even know what to do there. Or in the Q equal to 2 case, I don't even have a string in the asymptotic limit. It's really just the open string. So there, I don't know really what happens if you go into the bulk. I mean, that's if I don't even know the asymptotics. What is
Okay,
happening?
I'm not sure if I understand the asymptotic limit that you're taking. So maybe I could talk to you some other time about that.
Yeah, maybe.
But I guess I would say that the axion string certainly exists in 4D as a long semi-classical object. Like I can make
Yes.
a big loop of string, and I think we have reasons to think those obey the WGC bound.
Yeah, so I
Just
think
from the classical calculation of the string energy.
So what we're saying here is that you should view these strings more as the analog of supergravity strings in higher dimension. Like in 60, you have supergravity strings, and then I really don't know if I'm not in the asymptotic limit how to deal with them. They might be the states above the species scale, the super extremal states, but what I'm saying is that it's not like as simple as in the heterotic case where I have really.
It's certainly not that simple. Yeah, I agree. And I don't think I can say anything about the spectrum of short strings. But I think if the string is sufficiently long, I can just treat it with 4D semi-classical kind of physics, and then.
Well, but so my point here was like, okay, I actually, of course, I have this identity, like this correct behavior. But of course, this is not yet a proof that these states are actually super extremal. So we took this example and said, okay, do actually the order 1 factors match? And if we make this assumption that we have a perturbative string with particle-light excitation, it doesn't work. I don't know how to do it in the other case. That's my honest answer.
Okay. I mean, I think there are examples where these long strings are parametrically below the weak gravity bound, so it doesn't even come to order 1 factors. They just easily obey the bound. But the example that I was giving of the
D7 and D3, that's essentially what we had here, right? Maybe we can discuss.
Yeah, we can talk some other time.
Yeah, thanks, Max. Very nice talk. Let me try. So, have you tried to insist on the weak gravity conjecture and check what kind of quantization will work? So, let me imagine that.
We tried that, but then you actually run into problems that if you can like introduce some fudge factors here, but I mean, then depending on which limit we take, and if we take a primitive or non-primitive limit, it doesn't work. I mean, there's no unique choice. Depends on the limit which you take, and I think this is not really what one should do there.